Imagine if your AI assistant, never forgot a single thing you told it.
Hmm.
Not your weird coffee order, not that obscure movie you mentioned once, not even the really specific details of a project you discussed months ago.
Right.
What if it actually built on every single interaction, constantly learning and adapting, truly remembering? Because right now, that's kind of the holy grail for large language models.
Yeah, absolutely.
I mean, these engines are incredible, right? Driving so much of the AI we interact with. They can write, they can reason, generate amazing stuff.
Hmm.
But here's the big question, the one that keeps researchers up at night. What's still fundamentally missing, even from the most advanced LLMs?
Well, our sources point pretty clearly to one thing.
Which is?
A truly robust, unified way for them to remember. Memory. That's really the core of it. Current LLMs, I mean, they're brilliant in many ways, but their concept of memory is, well, it's very limited.
How so?
Most of their knowledge is hardwired, baked into their huge model weights during training. We call that parametric memory.
Okay, like their textbook knowledge. General stuff.
Exactly, their general understanding. Then there's what we call ephemeral activation memory. Think of that as their short-term scratch pad.
Fleeting thoughts.
Pretty much.
Yeah.
The context for the immediate question, but it vanishes right after, like a sticky note that gets wiped clean instantly.
Right. And what about things like RAGO, retrieval augmented generation? I hear about that all the time.
RAGO is helpful, definitely. It lets the model pull in external documents for context, but it's still more like an ad hoc textual patch.
A patch.
Yeah, like a quick lookup. It's not a deeply integrated memory system that manages information over time, or handles different kinds of data, or has rules about how long to keep something.
I see.
And this lack of a real structured memory system, it leads to all sorts of frustrating issues.
Like forgetting the conversation history.
Exactly. LLMs struggle with long, winding conversations. They can't easily adapt to new information you give them midstream. They forget your preferences over time. And maybe one of the biggest headaches is that knowledge gets trapped in these memory silos. Information from one chat doesn't help another app, even if it's the same user.
Okay, that makes sense. So that's where this new research comes in.
Precisely. And that's exactly what this deep dive is about, the groundbreaking new research on MemOS. It's a memory operating system designed specifically for LMs.
An OS for memory. Okay, intriguing.
Yeah. And our mission today is really to unpack how MemOS tries to elevate memory from just this fleeting thought
Right.
to what the paper calls a first-class operational resource. The idea is it could fundamentally transform how LMs learn, adapt, and truly evolve.
It sounds like a potential game changer.
It really could be. And to appreciate just how revolutionary MemOS aims to be, it helps to look back a bit, understand the journey of LLM memory research.
Okay, where did it start?
Well, our source traces this evolution through roughly 3 stages. Think of them like chapters. Chapter 1 was all about memory definition and exploration.
Just figuring out what memory even means for an LLM.
Pretty much. Researchers started classifying how LLMs could possibly remember. They looked at implicit memory, that's the knowledge baked into the weights from pre-training, or maybe refined later through knowledge editing techniques.
Okay.
And then they looked at explicit memory. Early on, this was often just, stringing together the last few turns of a conversation to give some context.
Like copy-pasting the chat history into the prompt?
Sort of, yeah. Or pulling in info from external databases, sometimes structured stuff like knowledge graphs.
So early days.
Yeah.
Classifying what's there, trying to stretch that short-term context window, like adding more pages to a really tiny notebook.
Exactly. Then came stage 2, the emergence of human-like memory. This is where things started getting, well, a lot more interesting.
How so?
Systems started showing signs of persistence, context awareness, even a little bit of self-reflection.
Ah, okay. Moving beyond just recall.
Right. Researchers started looking to biology, to our brains for inspiration. That led to models like Hipparag, trying to mimic the hippocampus for a better contextual recall, or Memory 3. Others, like PGAG and SecondMe, they focused more on achieving behavioral continuity, making the AI's actions feel more consistent over time, like it remembered past interactions or goals.
Okay, getting closer to a persistent self.
In a way, yeah. And that brings us to stage 3, which is kind of where we've largely been until recently. Systematic memory management.
More tools, more frameworks.
Exactly. More sophisticated tools, some even inspired by, computer operating systems, for actually manipulating memory. Projects like EasyEdit, MEMS, or OLEDA started popping up.
But still not quite there.
Right. Even these, while powerful in their own ways, still had pretty big shortcomings. They couldn't offer truly unified scheduling across all the different types of memory,
Uh-huh.
or comprehensive lifecycle governance, like knowing when to keep information, when to update it, when to archive it, when to just forget it.
Yeah, that sounds critical.
And they still struggle to let different AI agents or different user roles seamlessly share and fuse memory. There was still this frustrating fragmentation, these memory silos we talked about.
That really highlights a crucial shift in thinking, doesn't it?
What do you mean?
It's not just about building bigger LLMs that understand the world anymore. As AI gets more complex, multitasking, multi-agent systems, the LLMs need to do more than just process info.
They need to learn from experience.
Exactly. They need to accumulate experience, retain memory, and continuously evolve over time. And the current architecture is often built on those static parameters.
Yeah, the fixed weights.
They're just not built for that constant updating and personalization. It's like trying to teach an old dog new tricks, but the dog forgets everything by the next morning.
Precisely. And this leads directly to what the source intriguingly calls the next scaling law.
Oh, not just bigger models and more data.
Well, we've seen incredible gains from pre-training on massive data sets,
Right.
and then from post-training like alignment and fine-tuning, no question. But the returns from those traditional methods, they seem to be diminishing. The source suggests the next fundamental leap in LLM capability won't just come from scale, but from the ability to continuously model and schedule memory in a much more dynamic way.
Ah, so memory becomes the new frontier for scaling.
That's the idea. This concept, they dub it memory training, is exactly what MemOS is designed to enable. It marks a really profound shift towards learning and inference not being separate steps.
But a unified process.
A unified memory-driven process, yeah.
Okay, so we've got the problem, the history, the need for this new paradigm. How does MemOS actually do it? How does it make memory this schedulable core resource and break down those memory silos?
It starts by unifying 3 core types of memory, recognizing that each plays a different but vital role in an intelligent system's cognition.
Okay, what are the 3 types?
First is parametric memory. We touched on this. It's the long-term knowledge baked into the LLM's weights during training.
The foundational knowledge.
Right. The backbone for language understanding, general knowledge. It's deep-seated understanding of the world. And importantly, in MemOS, this isn't just static. It supports modular, domain-specific injection.
Meaning
Meaning you could plug in specialized knowledge, like legal or medical expertise, using things like low-ray-based modules. These are clever, lightweight ways to add specific skills without retraining the whole massive model.
Ah, okay. So it's not just general smarts, but you can give it targeted expertise, like making it a doctor who also knows law.
Exactly like that. Second is activation memory. This is more transient, the working memory generated, while the LLM is actually processing information doing inference.
The stuff happening in its head right now.
Kind of, yeah. Things like patterns and its hidden layers, attention weights. It's crucial for real-time context awareness, following instructions right now. The source gives this cool example of capturing a doctor's expressive patterns during a consultation. But here's the key part. MemOS can see which activation states are frequently used and transform them into more persistent forms. So those valuable real-time insights aren't just lost.
Okay, saving the important short-term thoughts. And the third type,
The third is plaintext memory. This is the explicit knowledge pulled from outside.
like the RAG stuff.
Yes, but potentially much more integrated. It includes documents, knowledge graphs, even specific prompt templates you might use. It's highly editable, shareable, and directly tackles the context window size limits.
So like the LLM's personal library or external brain.
That's a great way to put it. Examples they give are things like clinical knowledge and drug information pulled from a database. This plaintext memory serves as a flexible base for managing knowledge and continuous updates.
Okay, 3 distinct types: parametric, activation, plain text. Here's where, as you said, it gets really interesting. How does MemOS possibly unify these things that sound so different?
Yeah, this is the core idea.
You mentioned the memcube. What is that exactly? The source calls it the standardized memory abstraction and the fundamental encapsulation unit. Sounds important.
It is the unifying force. The MemCube is the true innovation here. It basically provides a consistent data structure and interface for all these heterogeneous memory forms: parametric, activation, external content.
So it puts them all in the same kind of box.
Exactly. Each MemCube holds the actual memory content, the semantic payload, and crucially, a whole lot of structured metadata.
Metadata like tags.
Yes, but much richer. This metadata isn't just descriptive, it's packed with intelligence, and it's organized into three main categories. First, descriptive metadata.
What's that cover?
Basic identification and its role. Things like timestamps, where it came from an origin signature like user input or inference output, and semantic types like user preference, task prompt, or domain knowledge. What is this piece of memory?
Okay, makes sense. Labeling.
Second, and this is really powerful, governance attributes. This is all about enabling safe and controlled usage.
Rules for the memory.
Exactly. Access permissions who can see or use this. Lifespan policies like time to live, meaning memory can automatically expire if it's, say, only relevant for an hour. Priority levels and compliance features, too, like sensitivity tags, watermarking, access logging for security and auditing.
Wow, okay. That's quite sophisticated management.
It is. And the third category is behavioral indicators. These are collected automatically based on how the memory is used at runtime.
Like usage stats.
Precisely. Things like access frequency, how often is this memory used, context relevance, how useful was it in recent tasks, and version lineage. How has this memory changed over time?
And why track all that?
Because these indicators are crucial. They don't just describe the memory, they actively inform dynamic scheduling. And here's a really cool part. They enable these transformation pathways between memory types.
Transformation pathways. Memory can change type.
Yes, based on those behavioral indicators.
Yeah.
For example, if a piece of plaintext memory, like a document snippet, is accessed really frequently, MemOS can automatically transform it into an activation template. To reduce the cost of constantly redecoding it from text, that's plaintext activation.
Clever.
Or if some knowledge from plaintext or even activation memory proves to be really stable and reusable, it can be distilled and integrated into the LLM's parametric structures.
Baked into the main model.
And essentially, yes, to boost core inference efficiency. That's plaintext activation to parametric.
Okay.
And it even goes the other way. If some parametric knowledge, part of the core model, is rarely used or becomes outdated, MemOS could potentially externalize it into editable plaintext.
Really? Pull knowledge out of the weights.
That's the idea, parametric to plaintext. This makes it much more flexible for updates, rather than being stuck in the model's fixed weights. It makes the MemCube, as the source says, a self-aware and continuously adaptive memory unit, constantly optimizing itself.
Okay, that MemCube concept is, wow, it's incredibly dynamic. So if the MemCube is this super smart, unified, transforming memory unit, what's the actual operating system, the OS part of MemOS? What manages all these cubes?
Right, the MemCube is the what, MemOS is the how. It operates with a modular three-layer architecture. The paper describes it as a closed-loop memory governance framework.
Like layers in a computer OS?
Exactly that analogy. At the top, you have the interface layer. This is the system's front door, how users or other AI agents interact with the memory system.
Through APIs?
Yes. It parses requests, figures out the memory-related intent, like retrieve this, update that, forget this, and invokes standardized memory APIs. They mention specific ones like a provenance API for tracking where knowledge came from, an update API for changes, and a log query API for tracing usage history.
And it understands natural language requests.
It has a component called MemReader, specifically for translating, our potentially fuzzy human inputs into structured memory operation chains. It can also handle complex workflows like query update archive, passing context between steps using these memcubes.
Okay, so that's the input-output layer. What's underneath?
Below that is the core,
Yeah.
the operation layer. This is the central control hub. It orchestrates everything.
The brains of the operation.
Pretty much. It has the mem scheduler, which dynamically picks the right memory type parametric, activation, or plain text based on the immediate context and needs. And it uses pluggable strategies for this selection.
Strategies like?
Things you might expect, like least recently used, LRU, but also more sophisticated ones like semantic similarity searching or matching based on those metadata labels we discussed.
Got it. What else is in this layer?
There's the mem lifecycle component. This models the memory's entire journey, like a state machine created, active, archived, deleted. And it supports really important features like version rollback and freezing mechanisms.
For auditability, like Git for memory.
Kind of, yeah, ensuring nothing gets accidentally lost or corrupted and you can trace changes. Then there's the mem operator, which actively manages the memory storage using things like tagging systems, graph structures, and multi-layer partitions to enable really efficient hybrid search across different memory types.
Okay, interface operations. What's the bottom layer?
Finally, you have the foundational infrastructure layer. This provides the sturdy support for reliable execution, making sure everything runs smoothly and securely.
What's included here?
It includes mem governance, just like the system's compliance department. It enforces all those access permissions, lifecycle policies, and maintains audit trails for secure operations. Then there's MemVault, which manages the actual storage. It handles diverse memory repositories, could be databases, vector stores, file systems, and gives unified access across different storage backends. So memory can physically live anywhere.
Making it flexible.
Very. You also have MemLoader and MemDumper for structured memory migration, moving memory between platforms or agents easily, making memory portable. And crucially, there's MemStore.
What does that do?
It supports open publishing and subscription of memory units. Think of it like a publish-subscribe system for memory.
So AIs could share memory.
Exactly, enabling seamless knowledge sharing and even collaborative execution across different AIs using shared memcubes.
Wow, okay, so you have these 3 layers: interface, operation, infrastructure, and it all connects.
Right, it ties together in what they call the closed-loop memory I/O path. So you, the user, make a request. That hits the interface layer, gets translated into structured API calls. This flows down to the operation layer.
Where the scheduler picks the right memory.
Exactly. MemScheduler picks the best memcubes based on context, strategy, metadata. That memory gets injected into the LLM's reasoning process. The LLM generates a response.
And then?
And then, crucially, the resulting state, maybe new insights or updated preferences, gets processed back through the operation layer tagged, maybe transformed by the mem operator. It's lifecycle managed and stored via the infrastructure layer for future use.
So it's a continuous cycle. Every interaction potentially refines the AI's memory. It's not just using memory, it's constantly organizing, governing, and archiving it.
That's the core idea. A continuous dynamic flow. It's like your brain constantly updating connections, only perhaps, as you said, much more organized.
But definitely more organized than mine sometimes.
Well, that's the goal anyway. So MemOS really isn't just a small tweak. It's presented as a fundamental shift. It provides this unified abstraction, the memcube, and this integrated management framework, the 3 layers, for all these diverse memory types.
And the aim is better reasoning, better adaptation.
Exactly. Enhanced reasoning coherence, because context is managed better. Better adaptability, because new information can be integrated smoothly. And improved scalability, potentially paving the way for true continual learning and long-term evolution in these AI systems, moving us closer to AIs that really do learn from experience day in, day out.
And the vision for the future in the source, it gets even wilder, right?
Oh yeah, they definitely paint a big picture. They talk about an entire intelligent ecosystem built around these modular memory resources.
Supported by concepts like
cross-LLM memory sharing. Imagine different foundational models, maybe one from Google, one from OpenAI, one open source model being able to seamlessly share relevant learned experiences via these memcubes. True interoperability.
that would be huge.
Then they mention self-evolving memblocks. These memory units that could actually optimize themselves over time, getting smarter about what they remember and how they structure it.
Wow.
And the really far-out idea, a potential scalable memory marketplace. A decentralized way to exchange validated, useful memcubes, like a global brain built from these tiny, adaptable, shareable memory units.
That's a lot to think about, a completely different way of conceptualizing AI knowledge.
It truly challenges our current view.
Yeah.
I mean, if LLMs can really transition from being these relatively closed, static generation systems,
Which is largely what they are now.
right, to becoming continuously evolving intelligent agents equipped with long-term memory, integrated knowledge, and behavioral plasticity.
Yeah.
What kind of truly dynamic, truly responsive AI experiences might you encounter in the very near future?
Yeah.
And maybe, more profoundly, what new questions does this level of AI memory raise? Questions about the very nature of learning, adaptation, maybe even identity, not just for machines, but perhaps reflecting back on us too.